Well, hi there, everybody. I thought we'd take a quick look at the group worksheet number 17 practice today. It involves reviewing a lot of material that deals with the rule of Pythagoras, the Pythagorean theorem, and other material. So I figured we'd take a quick look at that. So here we go. It was assigned as homework, and I thought maybe we should go over it quickly, so be sure that you understand everything. So let me share the screen here with the worksheet, okay? And we will be ready to rock and roll here. All right, so here we go. All right. Notice the directions were to solve the following problems, and you are to refer to this diagram, which of course is a right triangle. The right triangle labeled with angles A, B, and C, okay? And also the small sides A, lowercase a, which is across from angle A, lowercase b, which is across from angle B, and of course, lowercase c, which is across from, obviously, angle C, the 90-degree angle. So I thought we'd go through these questions together and take a look and see what we can do with them. Okay. Question 1 says, if angle B in this figure measures 70 degrees, which choice gives the correct measurement of angle A? Well, now if I go up here, if this is 70 degrees, we want to know what angle A is, which is the X. Of course, we know this is 90, right? And we know all the angles of a triangle have to add up to what? 180 degrees. Let me make this a better 90 here. So if I add these two together, that's 160 degrees of the 180 used up, correct? So therefore, what has to be left over out of 180? Well, you can see that the correct answer would be 20. So it is answer C. Okay, let's go on. Which statement must be true about the lengths of the triangle's sides? Now remember, look at the figure again. This is a right triangle. All right, the hypotenuse is side C, and we have the other two legs called A and B. All right, and we want to know which of these statements is true. What's the second choice? Is side C, the hypotenuse, twice the length of side A? I don't think so. Well, if I added the length of A to the length of B, would it add up to the length of C? You can tell just by looking at that figure that would never happen. So that's not going to work. Now, let me go back to A. I think it says A plus B is less than C. Well, I don't think so. If A and B added together would be greater than length C, A plus B can't be less than C. So it can't be A, B, or C. But look at D. Does that look familiar? D looks real familiar, doesn't it? It's the rule of Pythagoras, right? Or the Pythagorean theorem. The hypotenuse squared is equal to the sum of the two legs A and B squared added together. So our correct choice here is letter D. All right, let's go on. The sides A and C in the right triangle are referred to as its legs. Well, you already heard me mention that side C up there is the hypotenuse, right? So there's no way that that statement can be true. A is one of the legs, C is the hypotenuse. So this statement is definitely false, right? So that would be choice B. Let's go to our next question. The sides B and A in this right triangle are referred to as its legs. Well, yes, they are the legs of the right triangle, aren't they? Okay, they're the two shorter sides which kind of hold up the hypotenuse. Okay, so that answer is definitely true. So that would be choice A. The side A in this triangle is referred to as its altitude. Altitude is another name for the word of the height of the triangle, right? So how tall the triangle is using this as the bottom, yes, that would definitely be A, all right? So therefore, that is a correct statement. A is referred to as the altitude or the height of the figure in this particular drawing. So that should be choice A. Sorry about the clocks ringing, but I'm going to keep right on going. All right. Question 6. The side C in this right triangle is referred to as its base. Well, base, remember, usually means it's on the bottom, right? Does C look like it's on the bottom here? I don't think so. So B would be referred to here as the base of the triangle, particularly if A is the altitude. So that statement is not true. That is false. All right. Let me get that in here. I'm having trouble making this go up and down here. All right. So that is what? It is false. That is B. All right. A Pythagorean triple refers to a set of sides, lengths, in a particular right triangle which fit the rule of Pythagoras. In other words, if you put them in a squared plus b squared equals c squared, the statement would be true. If you take the same multiple of each of those individual sides of that triple, the resulting three numbers you get also should form a Pythagorean triple, right? So if I have an 8, 15, 17 sided right triangle, which is a Pythagorean triple, would it then be true that this group of sides, 24, 48, and 51, notice the 51 would be the hypotenuse, the longest side. So would this be a Pythagorean triple? Well, how can I figure that out? Well, you can see it's kind of related to 8, 15, and 17, right? In other words, if you take 8 and triple it, you get 24. If you take 17 and triple it, you get 51. So both 8 and 17 tripled give me the numbers that are in this particular supposed triple, right? But how about 48? Is 3 times 15 equal to 48? No, it's only equal to 45. So would this group of numbers most likely be a Pythagorean triple? Well, it appears not, right? So the answer to this would be no, which is choice B. If right triangle ABC above has a side A of 50 feet in length and a side C, which is 130, that of course is the hypotenuse, feet long, what must be the length of side B in this triangle? Well, to get that, I'm probably going to have to use the rule of Pythagoras, right? Unless I know a Pythagorean triple that goes with those, and you may not know what that Pythagorean triple is, so I'm going to write here along the bottom of this sheet here. Let me put these into the rule of Pythagoras. C squared has to equal A squared plus B squared, right? So if I take the side C, which is the hypotenuse, 130, and square it, and I add to it, all right, 50. Well, 50 could either be A or it could be B. It doesn't really make any difference. So, but if I square 50, right, and I add to it B squared, right, I should get 130 squared if I add those two squares that are on the right-hand side together. Well, if I square 130, I get 16900. Let me just double check that to make sure I haven't messed it up. But if I take 130 and I hit on my calculator x squared, I do get 16,900. If I square 50, I get 2,500, right? Now, how do I go about solving this? Well, I simply take b squared and isolate it, right? So I will take b squared and leave it here. I will subtract 2,500 off each side of the equation. So if I subtract 2,500 off of 16,900, I get 14,400, right? Would have to be b squared. So what would the value of b give me? I have to get the square root of this number, right? So if I go to my calculator and I go second x squared and put in 14,400, and hit enter, I get 120. So the side B, or the base of this particular triangle, should be 120. And you'll notice that it is choice B in question 8. So this is choice B. Does the answer you obtained in problem 8, when placed with 50 and 130-foot sides, give you a Pythagorean triple? Well, they're all numbers that come out even. They have no decimals in them. All right, they don't go on forever, any of the decimals. So the Pythagorean triple, okay, 50, 120, and 130 does exist. Is there a simpler Pythagorean triple that these are multiples of? Aren't each of those numbers, if you divided them each by 10, wouldn't we get 5, 12, and 13? Well, that also is a Pythagorean triple and a lower form of the Pythagorean triple, 50, 120, 130. But 50, 120, 130 still is a Pythagorean triple, okay? So much for that. All right, let's go on to part 2. All right, determine the answers to the following. Fill in the blanks. John knows that a particular mathematics principle is not correct. It's not always true. He knows the law doesn't work all the time. What need he only do to prove that he is correct? And notice I gave you big hints. He needs to come up with a single what? Remember, from the last test, it is called a counter example. A counter example. You'll recall we said the law could be stated that all prime numbers are odd. But the counterexample to that was the number what? 2, because 2 is an even prime number. So 2 is the counterexample. I'm sure you remember this from what we've discussed prior. Okay, let's go on. Circle each number which is not an example of the kind stated at the beginning of each row. So we want ones that are not the kind of numbers that are stated here. Okay, so let's have a look. I want numbers that are not integers. Well, 8 is an integer. Negative 1894 is an integer, right? But negative 22.95 is not an integer because why? It has a decimal on it. So that one is not an integer. This is not an integer. It's a rational number. It has a fractional decimal equivalent at 17/99, right? So it's a fraction. It is definitely a rational number, but it is not an integer. Integers cannot have fraction or decimal parts. Okay, 82 is an integer. This number here, negative 3.6985, definitely has a decimal part to it. It cannot be an integer. However, the last number, 2,569,873, is an integer. So those 3 that are circled are the non-integers. All right, look at rational number. We want numbers here that are not rational. When this is a fraction, fractions are rational numbers. This can be expressed as a fraction also because it's a repeating decimal. So that is a rational number. And 18.59 is 8 and 59/100ths. That is a rational number. This number here, 96.4545, 445, 4445, 4 4s and a 5, 5 4s and a 5, ... is what? An irrational number. Therefore, that number right there is not rational. So I've been circling the wrong things, right? I've been circling the wrong things. This is the number I should have circled because I should be circling the ones that are not rational. So I should have not circled any of these. I'm sorry, I was circling the rational ones, wasn't I? Oh, well, what are you going to do, you know? So I'll cross those off. All right. Circle any number here that isn't irrational. Well, you can see the first number is irrational, right? Because it has a growing pattern on it to infinity, okay? So can't circle that one, okay? Notice the last number has an arrow on it down here. See it? See that arrow right there? That's a Kellyism, meaning what? Goes on forever. It's all over the place as a decimal, right? No good. Or it is good. It is an irrational number, but I do not want to circle it because it isn't an irrational number, right? But these two definitely are not irrational. That's rational, and so is that. Okay, circle a number here that aren't real. There isn't a single number there that is not real. Those are all examples of real numbers. So I wouldn't be circling anything there, okay? All right, let's go to the next one, a natural number. Remember, the natural numbers are the numbers you learn to count with, okay? We didn't learn to count with zero. We didn't learn to count with negatives, okay? So the non-natural numbers here are this one, we can't have negatives. Otherwise, and this is a decimal, so it can't be a natural number. You didn't learn to count with decimals. So 0, -23, -41, and 7.39 are definitely not natural numbers. Now, in order to be a whole number, you have to not be negative. You have to be a counting number. Whole numbers cannot be negative because then a negative whole number would be an integer, all right? So 0 is a whole number, -2 is not, okay, because it's negative. This has a decimal on it, so it isn't whole. This has a negative on it, so it isn't whole. And this has a decimal on it, so it isn't whole. So, well, I may have confused you by asking you to look at the opposite of the situation, but you can see we can do that as well, okay? All right, number 12. Describe the decimal behavior of both an irrational number and a rational number. Let's do rational first, okay? So over here. If it's rational, right? If it's a rational, okay, it's a fraction, right? It's the quotient of two integers. How do they behave as decimals? They either what? Repeat or they terminate. Okay, that's all you really need to say. For your irrational numbers, okay, for your irrational numbers, what has to be the situation? They never repeat, they never terminate, right? But they can show a pattern, can show a pattern to infinity, all right? But they keep going, right? Okay, so there we go. We got that one down. All right, let's take a look at this crazy barrel problem. I gave you one of these before, remember? And we'll take a quick look at that. If you place $20 in a large barrel every hour for the next 30 years, okay, will you have accumulated a sum of at least $5 million in that barrel? All right, now we are to assume that there are no leap years and that you have a huge mother barrel, right? So let's see how we can get that. Well, I suggest you change 30 years into what? Money. So I would start with 30 years. I would put that over 1. The next step down is to get it into what? We want to get it to money, but the next step down from years is what? Days. We always go to days. All right? There's 365 days in 1 year. The year has canceled. The years have canceled. All right? Now what? Well, I want to get it into what? I wanted to get it into hours. Well, there are 24 hours in every single one day. So days would cancel here. All right. And now, what am I doing? $20 per every hour goes into the barrel. So $20 per every 1 hour. Hours would cancel. So you can see if I multiply 30 times 365 times 24 times 20, I get this answer. It is 5,256,000 and 3 zeros, excuse me. That's $5,256,000. So what would my conclusion be here? Yes, I will be able to save at least that much money. So we're good. Last but not least, the last question on here, can this particular number right here be shown to be a bank routing number? In other words, can we find a value for X that will allow us to have this as a bank routing number? Okay, so let's see. We multiply by 739, 739, 739. All right, that's 7, that's 3, that's 36, which is just 6. I'm going to cheat and take some shortcuts here. This is 7x, 6, 36, which is just what? It is just 6 upon 10, right? 49 is 9, 12 is 2, and 18 is 8. All right, so if I add all those numbers together and make out a sentence here, 7x plus some number has to equal 0 mod 10, right? Okay, so let's see. If I add these up, 7 and 3 is 10, 16, 22, 28, 37, 39. Looks like 39 and 8 is 47. Now, what number do I have to add to a 7 for it to end in a 0? I'd have to add a 3 to it, wouldn't I? So what number times 7 over here in the 7x position would end in a 3 if I'm only allowed to put a single digit down for x? I think most of you can see that 7 times 9 is 63. That gives me a number that ends in a 3. So x has to equal 9. So if you put a 9 in there for x in problem 14, you do have a legal bank routing number. And last but not least, let's take a quick look at the very last question. Why can't this number be written as or converted to a fraction? Notice that number is pi. And pi, remember, 3.1415927. It keeps going forever. It never repeats. It never terminates. It's an irrational number. And what do we know about irrational numbers? They cannot be expressed as a fraction, okay? Therefore, it can't be done. Well, thank you for allowing me to quickly go over this assignment. And would you please now move on to the next video? All right, you take care. I'll see you soon.